Hi everyone, since it happened kind of quickly at the end, I wanted to do two quick problems to show you how to solve differential equations using separation of variables technique. So these are the two differential equations I'm going to solve. I'm going to show you how to do it the way that abuses notation. So this is the way that is not mathematically justified, and then I'll show you how to justify it afterwards. So here's the way that's not mathematically justified. Let's get the 5y on the other side. So I've got dy dx equals 5y. So the way that is not mathematically justified is you treat this derivative as if it is a fraction. The dy and the dx are independent entities. We know that that is not true. We know that this is actually a single function, which is the derivative of y, and you can't treat it as two parts. But if you do, you can move all of the things that aren't y to the right and all of the things that are y to the left. So I'll multiply both sides by dx, and I'll divide both sides by y. So that gives me 1 over y dy and 5 dx. Okay, so if you write this, this doesn't mean anything. However, if you throw up some integral signs, this does mean something and is in fact mathematically correct. This follows directly from this previous step. And I'll justify that to you at the end of this video. I'll show you why these two things are the same as each other. But for the moment, I would say you're okay as long as you don't write that middle step. Alright, so from here, we're actually doing okay. So I know the integral of 1 over y. It's natural log, absolute value y, plus a constant. Except I'm going to collect all the constants on the right here. Integral of that is 5x. This constant that I've defined here is the constant of integration from this integral minus the constant of integration that came from this integral. So I just subtracted the constant over here, and I renamed it to be just a single constant. Alright, so I'm trying to find, remember the solution to a differential equation is a function y that makes this description true. So I'm still trying to find y. So let's exponentiate both sides. And I've got y equals e to the 5x plus c. And then this last step should be very automatic and swift for you. This is the same thing as e to the 5x times e to the c because of the simplification property of exponents. And now I'm going to rename e to the c. I'm going to redefine that as p. So this is now, and I'm going to move it to the front. So now this is p e to the 5x. So this is an entire family of solutions to my original differential equation, and you can check it by plugging it back in. If I wanted to actually work a problem involving this, in my problem I'll probably have some information about what y is and what x is. And so I can plug those in to solve for p, and then I can do some other stuff with it. Alright, what's this whole story look like for this other problem? So, same technique. I'm going to multiply both sides by y and both sides by dx. So now I've got y dy equals x cubed dx. This is bad. This is mathematically valid. So now again, let's just do both our integrals. So this one should be 1/2 y squared plus a constant. This one should be 1/4 x to the 4th plus a constant. And this constant is the collection of both constants. And now again, I'll solve for y. So I'll multiply both sides by 2. So that gives me 1/2 x to the 4th. You know, I'm just going to start numbering these constants. So this is constant 1. Constant 2 is twice constant 1. So when I multiplied through by 2, that became a new constant. And the only reason I'm doing this is because I don't want to keep track of, like, manipulating constant 1. All I care is it's still a constant. Alright, so now I'll take the square root. So I get y is plus or minus root 1/2 x to the 4th plus my constant 2. And there we go. So I've got another whole family of solutions to that equation.